No.
I was wondering who does that all the time. It's you guys. Sign in the wrong place. Okay, so I think the last place we stopped at was here, the Cartesian product. I don't think we actually did it yet. Does anyone remember? I think we covered all of this stuff, this weird long example, and then we're going to do this, but we stopped for some reason. All right, so the Cartesian product is where we stopped, and I think, yeah, it's pretty much one of the last things in the section. It's one of the places where you can bank on your marks because, again, this always comes out and it's just a simple rule to remember to write this thing. So I'll show you guys straight away with an example instead of going through the abstract stuff. So let's suppose I had two sets, and I'll just make these up. Do I have more space here? Let's just see. No, okay, so I'll do it here somewhere. Let's suppose I had a set A, which is given by 1, 2, 3, and another set B, which is given by, I don't want to write small a and b here because it gets confusing. So let me remember sets can be anything. So let me say beta and beta, right? Two Greek symbols. It doesn't matter what it is, right? Just an example. Okay, so if I asked you to write the Cartesian product for the set A and B, in this case, it's a standard thing. A cross B is how we say that. Okay, so the set which is firstly, it's just a set. So we open up a set bracket. Then we start making coordinates from the two sets. So it's going to be an open round bracket here. And the first coordinate that we take is from the set A. So it's the 1. It's the first one from set A. So that's our first coordinate. And then the other one will be the first one from set B, which is theta. Okay, and now we'll see the pattern here. I make another coordinate, again with the first one from set A, which is 1, but now the second one from set B, which is beta. Okay, and we just keep on doing this. Now we do this for the second element from set A, which is 2. So the 2 goes with the theta, then the 2 goes with the beta. So it's just same idea. Another third one, which you can probably guess, is going to be, I'll do it here at the bottom. 3 from the first set with the theta, and then the 3 with the beta. Then we close it up. Okay, does it seem straightforward enough to remember? Let me just keep that aside. That's one example here. Okay. So I'll give you guys a moment to look at a second example, which is done here. For the set A and B defined right at the top, the Cartesian product is given by this long line straight after that. We see we always take an element from the first set and then combine it with all elements from the second set. And then we do the same for the second element from the first set, and so on and so on. Does this seem okay for you guys? Remember? So you usually get a lot of marks for this. Sometimes they give 1 mark per element, which is a fair amount of marks. Okay. All right, so that's that. Now we cover very quickly Venn diagrams. These will be covered in more detail later on, but now we just cover the basics. So a Venn diagram is just a nice visual way to represent a set. We see an example right here of A intersect B. Okay, so in a Venn diagram, sets are represented as circles. The square in the background represents the universe, or the big set from which all subsets are taken. You've probably done this in high school, but I don't think the word universe was included at that time. So anyway, that is the big square, and when I'm saying square, the big rectangle in the background is the universe. The two circles are the sets that we are dealing with. And maybe this is one thing that's not said, but always assumed somehow. Okay, I'll explain this with the example. So let's try some examples. Already I think there's a mistake here because 1 and 2 look like the same, and 3 and 4 look like the same thing as well. So maybe let's just get rid of 2 and get rid of 4, since they're the same thing. Okay, so the assumption being made when you're asked to draw examples like this, the assumption being made is that all these sets overlap at some point, right? Because we don't know that unless we are told that. And if they don't overlap, then number 1, for example, could be written like this. I'll draw a big square. I'll draw A and B here with no overlap, and then that's it. And then I can't do anything, right? So this is not the way we do this, right? This is incorrect. Please don't take that down as a solution. That's not what we do. Even though they don't give us the information, we always assume that there is some overlap. Otherwise, there's no point in drawing these things. We don't need to visualize them like this. So the correct way to do that would be, the spot number 1 would be, first we draw the universe, then we draw the set A and set B, A and B. And now this is a union. So a union means we need to take everything from set A and everything from set B. So we just shade in everything from A and everything from B. Just shade all of that in. And that's the union of A and B as a Venn diagram. So that's number 1. Okay, number 3 is the same idea, except it's an intersection. And there's a different label there. The label is C. I'm just going to change that to B so that we're consistent. Again, it doesn't matter, right? It's just a label. So A intersect B is what we're looking at. So number 3 gives us, again, we always assume there's an overlap. AP. Now the intersection, remember intersections find common elements. So the common elements will only be represented by the overlap. So that's the part we shade in, the part which is overlapping. And that's the intersection. Okay, and 5 and 6, again, the assumption we have to make is that all these sets overlap at some point, which is not obvious, but we assume that if we are not told anything. So number 5 will be, we just need to draw somehow 3 circles overlapping. It doesn't matter how you do that, as long as you get them all overlapping. You can put 1 at the top and 2 at the bottom. That will do the trick. Or you can put 2 at the top, 1 at the bottom, 1 on the left, 2 on the right. It doesn't matter. As long as you have 3 overlapping circles, that's all we need. And then you label them, of course, A, B, and C. Okay, and number 5 asks for the union. So that means we just take everything. So we just shade in all of these circles. So I'll do that. Just shade everything in, starting from B for some reason, and then just go to A, shade it all in. Okay, if I lose anybody at any point, just let me know. That's 5. That's the union between these 3 sets. And 6 is just the intersection. So you can imagine I'll draw the same thing again, except now I just shade in the part which overlaps 6, because that's just intersection. So let me just do that as well. 6. And just to demonstrate, it doesn't matter how you draw these circles overlapping, as long as they overlap. You could also do it like this. You could draw 1 here, 1 here, one here, it really doesn't matter. A, B, C. Try and close that up. And this part in the middle, which is very small here, the overlap. Not the greatest diagram in the world, but I hope you guys can see what's happening there. Scroll down. I mean up. Okay. Yes. You're welcome. Okay, guys, the looks that I'm getting, I don't know if it's too easy or too difficult. Is it easy stuff? Okay. All right. So from Venn diagrams, we move on to sequences. Okay, so this section is not too long. We should finish it today. It's kind of similar to what you did in high school, except here we don't do the things where we find, geometric sequences, common ratio, common first difference, second difference, all that stuff. We don't do that here. Here we focus more on formulas that are already established and using them to compare them to other formulas or to calculate elements of a set. Sorry, not a set, a sequence, things like that. But that'll become clearer as we go on. So let's first start by defining a sequence, which is written up here. It's just an ordered list of numbers. So it's a bit different from a set, because in a set, order doesn't matter and repeats don't matter. Here, both of those things matter. So the order is important, and if you have repeats, you have to list the repeats as well. And we have some notation at the bottom here. We see A0, A1, A2, A3. All of these are just sort of like variables to represent elements of a set. Okay, so yeah, see, there's already a bit of a contradiction here, which I don't like. At the bottom here, okay, we can see this starts from 0 and goes upward, 0, 1, 2, 3. But here it's telling us that n is an element of natural numbers, which means starting from 1, which is not great, because it's starting from 0 on top. And this is also saying n greater than equal to 0. So this whole thing about natural numbers, that should probably be whole numbers, I guess, because it starts from 0. So let's put a W there for whole numbers. Okay, but anyway, the most important thing I'm trying to show you guys here is that these are just ways to represent a sequence. So for example, if our sequence was given by, I don't know, let's say 2, 4, 6, 8, and so on, multiples of 2, right? Then the way we'd represent these using labels would be A0 is equal to 2, A1 is equal to 4, A2 is equal to 6, A3 is equal to 8, and so on. Just labels to represent the elements in a set. Okay, so it can get a bit confusing because index starts from 0. So if they ask you to find the first element in the set, you will plug in n is equal to 0, not 1. So the first element starts from the index 0. That's the first element. Second element is index 1. So if they ask you, depends how they ask you the question. They might say find the second element, then you plug in n equals to 3. Or if they say find the element corresponding to n equals to 1, then it's much clearer. Okay. So these are the two main types of formulas we deal with here. The closed formula is going to be similar to what you've seen in high school, where you have a well-established formula where you can just plug in a value of n to get any element in the set. Right? I think you guys don't remember now, call it Tn, stuff like that in high school. You just plug n in and you get any element. So that's the closed formula. The recursive definition, it defines each element in terms of previous elements. So again, a bit abstract, but we will see what these look like. Let's start by looking at examples of closed formulas, and these will be shown right here. So again, we can see here, you just plug n into the formula and then you can get any element. So we'll look at the first one, for example, and see how it works. If I were to ask you to get the element in the sequence corresponding to n equals to 3, for example, then all we would do is just say n equals to 3, plug that into the formula, we'll get A3 is equal to 3 squared, which is 9. So 9 would be the answer corresponding to n equals to 3, which is, what is that now? Is that the fourth element, because we start from 0. So that gets a bit weird. Okay, and for the first one, if I asked you to list out a few elements of that set, starting from the first one, which is n equals to 0, then it would just be, okay, let me just do it here on the side. A0 is equal to 0, A1 is equal to 1 squared, which is 1, A2 is 2 squared, which is 4, A3 is 3 squared, which is 9, and so on. So that sequence would look like this. Usually we write it like this, AN double dot 0, 1, 4, 9, and so on. So that's how we represent that sequence more explicitly. So this part where I wrote A0 is 0, A1 is 1, all I did was just plug the corresponding n into the formula and get a number out. Maybe I should write here in case I'm losing anybody. This corresponds to n equals to 0, n equals to 1, n equals to 2, n equals to 3. Those are the values I plugged into the formula to get the corresponding numbers. Okay, am I losing anybody here? All right, so you guys will agree that it doesn't matter how complicated these formulas look. Like 2 is a bit more complicated, 3 is quite a bit more complicated. It doesn't really matter because all we do is plug n into the formula and then it's just calculator work from there. You don't have to show any working for these. So if I asked you, for example, with number 3, to work out the element corresponding to n equals to 5, just plug 5 in here and here, put this big expression in the calculator and get some answer. And that's it. You don't have to show any working or board mass or anything here. So it's straightforward stuff. All right, so that is the closed formula. Let's look at one example for the recursive definition. Now, I should mention the closed formula is ideal. It's what we want to get, but we don't always get these. They are harder to derive usually. The recursive definition is more easy to derive, but it's a bit more messy to work with. And here are some examples which are not written out very nicely. So I'm going to rewrite number 1 here at the bottom. It's A subscript n is equal to 2 A subscript n minus 1. And there's an initial condition here given A index 0 is equal to 1. Okay, so we'll look at those other examples in a bit. Let's take that out. And we'll just do this example. Find the first 3 terms for the sequence defined by this recursive formula. And I think it's clear here that each element is defined in terms of previous elements. So for example, A3 would be defined in terms of A2. Right, it keeps on going back. So you need to know a previous element to know the next one. All right, so if I say list the first three terms of sequence, in general, it's good to start from 0, even though that won't help us here. But we always start from 0, so I don't confuse anybody. And if it doesn't help us, we just discard that one. So for the first three elements, let's start from 0. Plug 0 into the formula above, and that becomes A0 is equal to 2A. At the bottom, we get 0 minus 1, which is just minus 1. Right? And firstly, is that part clear to everyone, what I did there? All I did is I took 0 and I plugged it into the given formula. Let's just make sure this is highlighted. This is the main thing. This is what we're always working with. I just took 0 and plugged it into that. Then at the bottom here, we get 0 minus 1, which is just minus 1. Again, just an index, just give us an indication of which element we are dealing with. But now we can't really work out A0 here because we don't know A minus 1, so we can't do much about that. So this doesn't help us. In fact, we don't need to know A0 here because we're already given it. We know what it is. So n equals to 0 doesn't help us in any way. So we just move on to n equals to 1, and let's see if we can do something here. Subbing 1 into the formula, we get A1 is equal to 2 times A0. And this we can work out because we know A0 is given to us as an initial condition. So I will just substitute A0 into here. It's given to us as 1. So this is 2 times 1, which is just 2. So now we're getting somewhere because we know A0, and now because of this formula here, we know A1 as well. So we can go on like this and work out another two elements. For n equals to 2, subbing that into the formula, we get A2 is equal to 2 times A2 minus 1, which is 1. And that is 2 times A1, which we worked out in the previous step. So we worked out A1 to be 2. So I will substitute that here. 2 times 2 gives me 4. So now I know A2. And by the same reasoning, I can now do the last one, n equals to 3. So subbing into the formula, n equals to 3, I will get A3 is equal to 2 times A to the power, not to the power, sorry, A subscript 3 minus 1. So that's just A subscript 2, which is 2 times A2 is worked out in the previous step, so I'll just substitute that back. It's 4, so 2 times 4 just gives us 8. Okay, so these are the elements of the sequence. If we wanted to, we could write them out in the way we did before, which is an double dot, and then just write the elements here. A naught is 1, A1 is 2, then 4, then 8, and so on. And so we could do that as well. Okay, so here we get, okay, before I move on, any questions before I move on? Yes.
Who is constant? That's not it. And For this change, exactly. I need to send me again. I'm sorry. She's
That's okay. So the question is, where does this come from? Okay, so we're always given one in the beginning.
How does it change to like what I need to decide what calculate calculate the number changes into?
Number it changes into. So it's just 2 times whatever A0 is. So 2 times 1 in this case. That's just a mathematical calculation. And the next is
Times 4.
this one here.
Yes.
Yeah, that's 3 times 4. That's because this one is given by 2 times A2. Is that okay? Why the A2 is there? Is that okay with you? It's all right. Okay. So maybe I can make it clearer by just showing here that in the first step, the A0 goes in here, then the A1 goes in here, the A2 goes in here. It's just recursively going on. Okay. All right, anyway, let's try another example. And this is more typical of an example that you will see in a paper. You'll be asked something along the lines of, given a recursive formula, find A6 in the sequence. And they'll give you some initial conditions. Okay, so there's a few ways you could try something like this. I'm just going to go immediately with the way that is quickest. But again, it's not the only way. So if you guys want to go around another way, it's okay. Okay, so first thing we do when we're given a question like this, again, it says find A6. Then we first start by writing down formula. Because AN is equal to 2AN minus 1 minus AN minus 2. And our initial conditions are given here. A0 is equal to 3. A1 is equal to 4. So we could do what we did the last time, which is start from n equals to 0. But maybe we realize now at this point that n equals to 0 is this element right here, which we know already. Right? A0 corresponds to n equals to 0. So we don't need to start from there because we know that one already. N equals to 2, sorry, n equals to 1 is the next one. That gives us A1, which is known already. So usually we start from n equals to 0, but we don't need to because we know already that corresponds to A0 is equal to 3. That's given to us. Right? And for n equals to 1, A1 equals to 4. That's known, that's given to us, so we don't need to work these ones out. We could list them here like this, but you don't have to even do this. I'm just doing it to show you the order of n. So these first 2 steps are already done. Now we can just keep going up until we reach n equals to 6 to get A6. Okay, so let's do that. Let's go to n equals to 2. So for n equals to 2, what's going on with this thing? All I do is I plug n equals to 2 into the formula above, which gives me A2 is equal to 2 times A subscript 2 minus 1, which is 1, minus A subscript 2 minus 2, which is 0. Okay, so very important that you guys are okay with how I get this formula here. Just by substituting n equals to 2 into the above formula. Is that okay with you guys? Are you losing anybody on this part? Yes. The question.
Why does that happen to that in the outcomes of the outcomes of the outcomes?
So say again.
That's happened for the most one, I think, because we know the outcome of the study. And my dad, this.
Yes. Okay, so you guys all okay with that formula? Okay. I take no response to me, yes. Okay. All right, so from there, it's just a matter of plugging in known values into the formula. We know A1 that's given to us above. We know A0 that's also given to us. So we just plug those numbers into the formula. Here we get 2 times A1, which was given as 4, minus A0, which is 3. And this is just something you can do in your calculator. I mean, you can work these out in your head, but in a test exam, just always don't trust yourselves. Use the calculator, because I see people going off by 1 or 2 on either direction. So just be safe. So this is a 8 minus 5 minus 3, sorry, which is 5. So that's A2. So now we know A0, A1, and A2. We can go ahead all the way to A6. Okay, so I'm just going to go ahead. N equals to 3. A3, this is again according to the formula above. According to this formula here, A3 is equal to 2 times A2 minus A1. And we know A2 and we know A1, so we can plug these in and get a number. This is 2 times A2 has worked out to be 5. A1 was given as 4. So this is 10 minus 4, which is 6. Okay, I'm just going to keep recurring and doing this up until 6. So let's go for it. N equals to 4. We get A4 is equal to 2A3 minus A2. And we know A3 and we know A2, so we can plug these in. A3 we worked out to be 6. A2 we worked out to be 5. That's 12 minus 5, which is 7. Yeah. All right, 2 more to go. If you guys see me making a very stupid arithmetic mistake, just correct me. N equals to 5. Here we have A5 is equal to 2A4 minus A3, which is 2 times, we worked out A4 to be 7, we worked out A3 to be 6. So that's 14 minus 6, which is 8. 8. Okay, and I think we can see a pattern emerging already. But anyway, let's just go since we're almost there. One more step. N equals to 6. A6 is equal to 2 times A5 minus A4. Minus A4, which is 2 times A5 is worked out to be 8. A4 is worked out to be 7. So that's 16 minus 7, which is 9. Okay. A6 is a bit much, but anyway, repetition is always good for practice. So this one here, 9 right at the bottom, that's our answer. That's A6. Was the question to work out the sequence or the element? I don't remember. Let's go back and check. Find A6. So we just need to find A6 and be done. Okay, questions, comments, complaints, anything? Okay. Then now we get to the last question in sequences before functions. Okay. Let's just see. Okay, so guys, this question here is a little bit of a brain teaser. It's a little bit of a, you have to sit and think about this one. Do you guys want to break before that? Yeah. Yes. Okay, so 15 minutes, so come back at 5 to 11.